I ask the speakers to be online and visible and ready to answer questions and discuss some of the topics. So we had a very, very good diversity of presentations, of perspectives, of robots also in our talks. So I'm sure that we can we can raise many questions. So I tried to go through the questions that have been posed so far. Not sure can manage everything, but Veronica is helping me. Thanks a lot. So the first one is actually pretty technical question to me. What a simulation environment for the octopus arm, and that's a very special simulation environment. It's actually a modeling framework that I cited in my slide that is called LifeX, and it was developed by Politecnico of Milan in Italy. So good question, because I know it's pretty difficult to have modeling and simulation frameworks, and we had this opportunity through this collaboration. And then the other one is also for myself. If the octopus inspired hand is not really hand, consume less energy than modern robotic hand control systems, that's exactly the idea. This is exactly what we are demonstrating, that embodied intelligence actually simplifies control and reduce the energy needs. Okay, there is another one on still a hand. I don't know if it's for me or maybe for Kento. If I want to build a robot hand similar to the human hand, will it consume more energy and also will be efficient under every environment? I didn't get the point of the question here, so maybe Hongwei, do you want to try to reformulate and and make a reference also to which presentation? Okay, let me go through the weight. And there is something for Hongying. It's not a question, it's just a comment, because it's in the Nicholas Gold from UCL has developed cardboard based modules as alternative to Lego. Maybe you know the work already, but I don't know. Yeah. Okay. I don't have any other questions from in the queue, but I encourage everyone to raise points. Can be comments, not necessarily questions. But of course, I have my own. So if I don't see any other from the audience, I will go ahead myself. I have some for Kento, please. Because I mean, your robots are amazing. I'm especially now referring to the tendon-driven musculoskeleton humanoids, because there is a lot of compliance there. So I think there is a lot of embodied intelligence in some dynamic tasks like walking or running or others. So I would like to understand to what extent you reduce the complexity of the control system thanks to the compliance, because you have so many actuators, so ideally so many control parameters, but also this compliance, I think it helps a lot.
Thanks. So it's actually a very difficult question, because yes, so we are making the very complex, very human, embodiment, like musculoskeletal humanoids. But at the same time, of course, there's a lot of the actuators, sensors, 124 motors, and a lot of the contact sensors, and also the motor has the muscle tension sensor, thermometer, and of course the muscle tension sensors. And yes, I must say that it's very difficult to think about how to reduce the energy costs. Actually, I'm not researching about this. So because this kind of robot is very complex, and only for the engineering, it's very difficult to construct the robot. And yeah, of course, now the usual control of this robot is just a neural network. And we train the relationship, the neural network of the relationship among the muscle tension, muscle length, vision sensor, and joint angles. And then we can use the neural network to control the joint position over the end effector, using the muscle tension control or muscle length control. But sorry, I can also say about how the energy is reduced by the compliance of the muscles. But of course,
I'm
the
sure, yeah, it is.
engineering is super difficult, and we stop at them. And yeah, we are always thinking about the collaborators of the embodied, the more like the embodied intelligence with
So
sorry.
Because I saw a question popping up about this same topic. So it's for you. You have mentioned that there is redundancy in the actuators. Does it come from using motor synergies like that commonly applied for hand control? Where does the redundancy come from?
So what the redundancy comes from? Well, what do you mean, one more time? So you mean?
Because you mentioned redundancy in the
Yes.
actuators. So the question is, what kind of redundancy? Where is it?
Redundancy. So now the redundancy itself is the redundancy of the muscles. As I said, of course, even if one muscle is ruptured, the musculoskeletal robot can continue even if one muscle breaks. So I think it's one of the redundancy. Of course, another one is the redundancy is by utilizing the redundancy, muscle redundancy, also and the nonlinear elasticity of the muscles, the robot can do a variable stiffness control through hardware, and it's great. Of course, I think it's very close to the human beings, and the humans can control the hardware stiffness by the muscle stimulation, and this is one of the redundancy. I think the redundancy has a lot of the meaning in the musculoskeletal robot. Yes.
Yeah, and another simple question for you, then we probably change topic. Why do you have a robot that can sweat? So why is it for cooling the robot, and how efficient
Yeah, of course.
is it?
Is it for curing?
Yeah.
Yes, the evaporating curing is, I think it's not my own research, but my colleagues' one, but I don't know why, but I think it's super cool, right? So yeah,
Yes, it is.
I don't, so we don't want to narrow the space of the embodiment. I mean, the human embodiment is great, and the human can add a lot of things, but of course now the robots cannot do many things. So if we design the robot with our own thinking, maybe the very design will be very biased. But the current robot is not good. Is not very close to human beings, and human beings can do a lot of things. So that don't narrow the design, and firstly, they closely mimic the human beings and explore why the humans can do very well rather than robots. And I think it's very important. And this sweat mechanism is one of them.
I have another point on humanoids, but I keep it for the end. So let's switch to Jonas' talk. So in terms of aesthetics, do you find that human beings are resistant to any particular features of the robot's appearance being fully humanized, or is close proximity to human-like appearance and behavior preferred?
Yeah, that's a
Which
very good
relates
question.
also to Kento's work.
Yeah. There's some overlap there.
Humanoid robots. Yeah.
I think that the soft robots that I've experimented with, they are so far from humanoid robots that they have very different body plans and so on. And in general, I find that in the experiments that we have done, human likeness is not something that contributes positively to the impressions of the robots. Usually it's something that we haven't studied it systematically, but the kind of comments that we have gotten suggest that it's something that doesn't benefit a robot unless it's also more human-like in other aspects. but it is something that that is also relating to perhaps this kind of balance between, if you have soft robots, then you automatically have this kind of biomorphic appearance, but then should you kind of emphasize that, or should you downplay it, or should you combine it with more mechanical features? And if you do so, then how can you do it naturally? And our work so far suggests that there's a kind of trade-off, there's a kind of balance that needs to be met, so you shouldn't make it too close to the natural thing, because then it can also become uncanny. But if you make it organic or biologically appearing to some extent, then you can also get something for free, in terms of people appreciating interacting with it, and being kind of open to treating it more like an agent than just an object. So that's the kind of the place that we are at now.
There is another interesting point about your study on aesthetics. If you investigate the role of touch
Yes.
interaction
Yeah.
as well.
That's a very good question, and in fact, I'm leading a network right now that focuses on touch, but still in the early phases. But we have done some studies where touch has been a part of it, and we have some findings that suggest, for instance, that there is a difference in how people touch soft robots and how they touch traditional robots. And one of the findings was that in this study with the tentacles, for instance, we found that people, they kind of know how to interact with traditional robotics technology, whereas they are not completely sure when it comes to soft robots. So there seems to be kind of a bipole division, where some are very, very careful because they think, oh, the robot is so fragile, we need to take care of it. And others, they kind of treat it like a garden hose or something that you can just bounce around, or that can kind of withstand anything because it just is compliant. Yeah, so I think that, that there's a lot more to be done on that. And also one of, just I'm gonna end up now. Just one point is also that I think what we see is also that there's a connection between the assessment of touch and other modalities such as the appearance. So I think these should be really designed together.
And another point is, if you consider how media, like film, movies, television, aestheticize robotics, and how that might influence the human perception of robotics.
Yeah, I think that is also relevant in relation to soft robotics, because we know, of course, there's the Baymax character that a lot of people know and kind of associate with soft robotics, but a lot of people also just think about either humanoids or manufacturing robots when they think of robots, and then soft robotics is something completely different and unexpected if you were expecting something like that. So I think that of course contributes to what people read into it and what they expect when they encounter a soft robot. And we actually also used this film and television as a kind of resource for our some of our design work, where we wanted to add sound to a soft robot. Then we actually looked at movies that had fictional soft characters and what kind of sounds they made, and we tried to replicate that for some of our soft robots.
So there can be biases, right?
Definitely, yeah.
Depending on the culture. So in different parts of the world, it's also different. In some cases, a positive bias. In some cases, it's a negative bias, right?
Yeah.
Yeah. Okay, so I go back to the question on the hand. So the question was reworded. So if the hand closely mimics the structure and functionality of the human hand using soft robotics technology, will it be more energy efficient than traditional ones? So my short answer is yes for me. I mean, to the extent that this mimicking means that it can adapt with embodied intelligence to the shape of objects when grasping. So if this is the case, in my opinion, it will be more energy efficient. And there is a second part, which is can such a design perform efficiently in complex and diverse environments, including varied temperatures, humidity levels, and mechanical stress, compared to conventional rigid robotic grippers? This is more difficult for me. It depends on how you actually design this human-like hand and with which kind of rigid robotic gripper you compare to. So I don't have a clear answer here. I don't know if anyone else can try answering. Meantime, I scroll down. Okay, I think okay, there is one question for Hongying. So regarding the Lego-like origami, do you envision them to be also easy to build by naive users? So non-expert users.
Yes, the answer is yes. Because actually for the origami pattern, right? I mean, you can download it online from our paper or somewhere, and then you the only work you need to do is you just like a 3D print or use some lamination technique to just bond it with an airtight fabric, and afterwards you fold it and then you seal it, and it will be a block that is usable for you. I mean, actually, you can just fabricate one maybe within 1 hour. I mean, it depends on your your efficiency. If you are already very familiar with everything, I mean, it can be even faster.
Excellent. Very, very cool. So for pneumatic soft robots, is there any efficient simulation software where it is possible to integrate sensors and AI? Well, this is a big question. I don't have very positive answers. So do you have any, maybe Hongying? Because there's several software tools, but none of them is so complete, right?
Yeah, I don't think we have such a mature software yet, because normally if researchers simulate the pneumatic soft robots, we may use some FEM software to simulate the deformation. And then for that one, I mean, not AI algorithm integrated yet.
Yeah. So if there are no questions coming up, I want to go back to my question on the humanoid robots, because I mean, I love your approach. Kento is amazing, and I think, I mean, that during the years you showed a little bit of history of humanoid robotics in your institution, but there are also other institutions, especially in Japan, that made really long pathway, learning a lot and coming up with solutions like yours, with a lot of compliance, and then at some point, suddenly for me at least, many companies started producing humanoid robots. That was pretty unexpected to me, at least, no more really in the field. And I was a bit surprised. And my question is, are they using all the lesson learned by us, by scientists, by universities when they build the humanoid robots, or they just use more traditional robotics technology?
Okay, so you mean about the upcoming, the very many, the humanoid, the company?
Yeah, the Unit 3,
yes, is it
even
using traditional or of course now it's very emerging. The technology is always used. So of course the Unit 3 or any other humanoid robot is always working by the just reinforcement learning. Of course, maybe country not any the humanoid companies using the traditional classical control, so only using the reinforcement learning, and sometimes the PBO, teacher student policy, and the Isaac Shim, and this kind of GPU accelerated simulation. And yes, so yeah. So what's the point?
Yeah, I have the feeling sometimes that that I don't know, they took a step back compared to what universities, I mean, the advances of universities in the field of humanoid robotics. So, but on the other side, they have the power of being companies, and I mean, having big investments, and probably, as you say, investing a lot also on the AI that they put inside the robot. So they give this demonstrations, but yeah. it's a big question. So what our role
it's a big question, and
become?
what our role is about the humanoid
because
community. So yes, I think about the musculoskeletal humanoids, I think it's rarely done by the the humanoid company. So I think there should be many contributions. But about the usual humanoids, yes, it's very difficult to have the unique contribution to the humanoids, the companies, you know. And but of course, this kind of the soft robotics community, like the more cross-field embodied intelligence, is very important now. And usually, of course, the humanoid robot is now trained only in the simulations, and there is no of course, there is zero shot sim to real, so there is no the actual exploration inside in the real world. And of course, when current robot is of course stiff, and if it falls down, it's very dangerous. And of course, the manipulation is not so good now. And I think the human like the very soft the skin and the very soft the body is more important if the humanoid robot goes inside of the home, the not industry, but the more home. So I think house is, and I think we can have many contributions about it. So how to make robots soft and how to train, not in the simulation or not in the real world. So yeah, but now of course, I'd say that the flexible body is also currently easily simulated in the simulation. So I don't know if the only simulation is okay, or the real world the exploration is actually necessary. So I think this is the thing with your octopus robots. So how do you think about it?
Yeah, especially if we want to, to put embodied intelligence at the center. Of course, the experiments with real prototypes, with real interactions with the environment are very, very important. Yeah, absolutely. Just wish to thank Leone for the comment when we were discussing about the simulation software. He mentioned SOFA. Of course, many of us work in soft robotics. We use it. Yeah, we know there are a few, but yeah, not yet one that is the optimal one. Okay, any
for Kento?
Of course.
Yeah. Hi. Yeah, very amazing work. I mean, just curious about, as you said that you are now working on design a new musculoskeletal humanoid robot. So for that one, is it still cable driven or you use a different technique?
It's cable driven, of course.
Cable driven.
Yes,
Okay.
cable driven, and the difference is, of course, the musculoskeletal humanoid robots muscles is just a very thin wires. So, but I think the more the human-like embodiment, it should be volumic, like a human body. So the volumic, the human body, and also the liquid inside the joint capsule. They can sense the pressure between the bones, and there are a lot of, and also usually the robots, the musculoskeletal robot has only muscles, but of course the ligaments is very important to stabilize the movement, and the ligaments inside. So now that we are exploring the human-like embodiment from the ligaments, tendons, of course, the sweat mechanisms over the volumic muscles, the many aspects. Yes.
Okay. I mean, to build this musculoskeletal humanoid robots, is the most challenging part come from the hardware design, or is it come from the control, or both are very challenging?
Of course, both of them. But yeah, usually it is very difficult to construct the musculoskeletal humanoids alone. So it's very difficult. So I mean, each part is made by each person, and after that it should be integrated, and the integration part is very difficult, of course. And yeah, and of course the control part is too difficult. Now about the kangaroo, the 124 motors inside, but so of course it is there, the coordinated seamlessly. And yes, before, I think before 2000, the 11, the 13 or 14, there was no the controllers using the neural networks. So the how to run the relationship among the joint angle, muscle tension, and muscle length was very difficult. We are using just the data table and how to update the data table. But of course, there are a lot of muscles, and it's very difficult to have a database of that. And yes, so it was very difficult. But now, of course, we have the easy technique like the neural networks and also the imitation learning or something. And by using them, I think now it's gradually becoming well. But only if we only train the neural networks, the robot can know the relationship among sensors, but it can just control the end effectors. But the difficult part is more like the dynamic motion, like the walking or the more precise manipulations or dynamic manipulations. But about it, the musculoskeletal robot is super complex, and it's very difficult to make it inside of the simulation. Of course, if we can, we can make the simulation. Yeah, we have a musculoskeletal robot simulation in Mujoko. And of course, in Mujoko, we can simulate the tendons. But of course, if we make it and apply the reinforcement learning, everything is different. And sim-to-real is currently impossible. So there is a friction, viscosity, and of course, sometimes a muscle wrapping around joints. And it was very difficult to simulate the robots. And now, we are seeking the new methods and how to do this kind of reinforcement learning in the real world with the musculoskeletal robot.
That's awesome. And the follow-up question is like, I'm not sure whether you follow a startup company called the Clone Robotics.
Clone, yes.
So because actually they just use the I think their actuators are just mid-cable muscles or muscles similar to mid-cable muscles. I mean, how do you comment their design and your cable-driven design?
Yes, it's good. So of course, this kind of the Makiben muscle-based musculoskeletal robot exists from the very old days. So like of course in Japan, there are a lot of people using the Makiben muscles for the humanoid robots. But yes, and of course Clone is doing it. But of course the Makiben muscle is very difficult to control. And yes, of course, just to control the tension control is okay, but of course there is hysteresis, and sometimes there is a latency, and the position control is very difficult. So of course, just for the manipulation, I think it's okay. So like the dynamic manipulation itself is okay, but the static manipulation is very difficult, and also the balancing is super difficult, I think. And I don't know what happens, but I think the Clone's robot is sufficiently complex. I mean, if there is a great training, the running policy, the technique, I think it can work and it can do a great manipulation. The complexity is, of course, sometimes cumbersome for us, but I think there is the space for the improvement, and we can make a great robot if something happens.
I see more questions popping up, but we are also close to the end of this session. So if you have very short answer, the first one for Kento, do you think a hybrid could be prospective? Hybrid meaning tendon-driven plus pneumatic.
Yes, of course it's great. So I think usual joint, I think rather than the tendon-driven robot, now the motors, the technology is very developing fast and fast speed, and I think hybrid is one of the options. And also we are thinking, yes.
Short answers, Hongying.
Oh, sorry.
You said that your Lego like blocks are pneumatically actuated. So the question is, did you find strategies for reducing the number of valves and external components?
Yes, the answer is yes. Actually, we just submit our paper to the Arrows 2025 is under review. And in that work, we are managed to control N square soft actuators just using 2N input signals. And all these soft actuators can generate independent output configuration. And in our demonstration in that paper is like we control 24 artificial muscles using 10 input signals. And these 24 artificial muscles can generate more than 950 independent configurations. I mean, I hope we can see the work.
Excellent, I know the work, and I think it would be a great contribution to our community. We have a question from Fumiya who cannot be answered with a quick answer, because he's wondering what is the importance of high-level cognition computation, like planning, decision-making, spatial cognition for the soft robots? Is it too early to talk about such a question? No, absolutely, it's not too early. It's absolutely to the point. If I can give a short answer, as I showed in my slides, and also last year in the same conference, I tried to say that we have to put back the embodied intelligence part into the full picture, because we tend to focus on that part only, which is great, because I mean it gave us an excellent insight to build new robots. But yes, we should take the full picture into consideration, for me, including the cognitive part. I don't know if the others have other answers to give to Fumiya.
I agree. I think that combining the two is probably relevant in most cases.
Okay, there is another small comment from Pablo Valdivia, which is similar to the question I already asked to Kento. So how your robots different from the commercial options like those produced by Unitree, Atlas, and so on, and similar. So you probably already asked, but you have just one quick final point on this.
It's very difficult to say one point, but variable stiffness, the redundancy for the continuous movement, or many things. Thanks.
They are different, and they are better, in my opinion. And what we discussed, Pablo, was are the companies taking into account the lessons that we learned in research, in academic research, or not? But we don't have an answer, of course. So that's a very good point to close our discussion. Perfectly on time. It's now the end of the session. So there is a lunch break.
Yes, thank you very much, Cecilia. I think this was a fantastic panel session, and thank you all speakers for the very active contributions. And this soft robotics is a really new frontiers on the embodied intelligence, and I think this is probably the latest from all the cutting edge research at the moment. So let's continue this discuss this point throughout the EI conference this year. And then I think it's going to conclude this session. Thank you, Cecilia, for chairing this session. And then thank you very much.
Thanks.
Okay, now I think we need to move on quickly to the breakout session. So I think Veronica is going to open the breakout sessions now, and all the speakers assigned to the breakout session, please move there, and the chair of the session is going to coordinate with all the speakers. Okay, so thank you very much for the morning speakers so far, and enjoy lunchtime and breakout session. Okay, thank you very much. See you later then.